Welcome to this coding walkthrough. Today, we'll explore an interesting problem titled Most Frequent Number Following Key in an Array. In this problem, we'll dive into how we can efficiently identify the most frequent number that occurs after a given key in an array. Let's get started. In this problem, you're given a zero-indexed integer array called nums and another integer key. The task is to identify a key following number, which is any number that immediately follows an occurrence of the key in the array. Among all the key following numbers, you need to return the one that appears most frequently. If there is a tie, meaning multiple numbers have the same highest frequency, the smallest number among them should be chosen. The input consists of the array nums with a length between 1 and 1000, and all values in the array as well as the key itself lie between -10,000 and 10,000. The output is simply the number that meets these conditions. To understand this better, let's look at the first example. Here, the input array is nums equals 1, 100, 200, 1, 100, and the key is 1. The key appears at indices 0 and 3 in the array. The numbers that follow these occurrences of the key are nums, 1 equals 100 and nums, 4 equals 100. Since the number 100 appears twice as a key following number, it is the most frequent. Therefore, the output is 100. In this case, there is no tie, so the answer is straightforward. Now, consider the second example where nums equals 2, 2, 2, 2, 3, and the key is 2. The key appears at indices 0, 1, 2, and 3. The numbers that immediately follow these indices are nums, 1 equals 2, nums, 2 equals 2, nums, 3 equals 2, and nums, 4 equals 3. Here, the number 2 appears 3 times as a key following number, while 3 appears only once. Since 2 is the most frequent, the output is 2. Notice how the frequency determines the result, and ties are resolved by selecting the smaller number, though that is not needed here. Lastly, let's review the constraints and some keynotes. The array length is guaranteed to be at least 1 and at most 1000. Each number in the array, as well as the key, is within the range of -10,000 to 10,000. Importantly, the key is guaranteed to appear at least once in the array, so there will always be a valid output. A key following number is strictly defined as the number that directly follows the key in the array, and when there are multiple numbers with the same frequency, you must choose the smallest number. These constraints ensure that the problem is well defined and solvable for any valid input. When tackling this problem, the brute force approach is the most straightforward method to consider. The primary idea is to traverse the array and focus on each occurrence of the given key. For every instance of key, we check the number that comes immediately after it in the array. To keep track of these numbers and their frequencies, we use a dictionary, where the keys represent the key following numbers and the values store how often each number appears. Once the array is fully traversed, the next step is to find the number with the highest frequency in the dictionary. This approach is efficient, as it only requires a single traversal of the array, giving it a linear time complexity of O(n). The space complexity is O(k), where k is the number of unique key following numbers, since we need to store these counts in the dictionary. The brute force approach is effective for smaller datasets, but it can be improved to handle larger arrays more efficiently. Instead of separating the frequency counting and finding the most frequent number into 2 distinct steps, we can combine them into a single iteration. This leads us to the optimized approach. Here, we initialize a dictionary to count the occurrences of key following numbers as we traverse the array. At the same time, we track the most frequent number and its highest frequency dynamically, which eliminates the need for a second pass through the dictionary. This optimization not only reduces the computational overhead but also simplifies the implementation. The optimized solution retains the same linear time complexity of O(n) and space complexity of O(k), but it achieves greater clarity and efficiency. The optimized approach offers a clear advantage by streamlining the process into a single iteration, making the solution both simpler and more efficient. While the brute force method is functionally equivalent in terms of time complexity, it involves redundant steps that can be avoided. By simultaneously counting frequencies and maintaining the most frequent number, we reduce unnecessary work. This approach was chosen because it strikes the perfect balance between clarity, efficiency, and simplicity. A key insight that makes the optimized solution so effective is recognizing that the counting and max frequency finding steps can be merged. This eliminates the need for additional passes, creating a more concise and elegant implementation. The solution to this problem relies on a few key observations. First, the only numbers that matter are those immediately following the given key, so we can ignore all other numbers in the array. Second, using a dictionary is an ideal choice for counting frequencies, as it allows for constant time operations. Finally, combining the steps of counting and max frequency tracking minimizes redundant computations, leading to an efficient and streamlined algorithm. While alternative approaches exist, such as using an array instead of a dictionary, these are less flexible and require additional assumptions, such as knowing the range of possible numbers in advance. The optimized approach stands out as the best choice because it balances performance, clarity, and general applicability, making it a robust and elegant solution for this problem. In this problem, we are tasked with finding the number that most frequently follows a given key in an array of integers. If the key is not present in the array, or if no number follows it, we return an appropriate result, such as -1 or null. To approach this systematically, let's start with a brute force method. The core idea is to iterate through the array, locate occurrences of the key, and count the frequency of numbers that immediately follow it. To achieve this, we use a dictionary to efficiently track these frequencies. Additionally, we maintain a variable to record the highest frequency observed, as well as another variable to store the number associated with that frequency. This ensures that by the end of the process, we have the correct result ready to return. Now, let's break down the brute force approach further. First, we iterate through the array, but only up to the second to last index to avoid accessing elements out of bounds. For each element, we check if it matches the given key. Whenever a match is found, we look at the number immediately following it. This number is then added to our frequency map. If it already exists in the frequency map, its count is increased by 1, otherwise, it is added with an initial count of 1. After updating the frequency map, we compare this number's frequency with the current maximum frequency. If it exceeds the maximum frequency, we update both the maximum frequency and the result variable to reflect this new number. To handle special cases, such as when the key is absent or the array is too small, we return -1 or null as appropriate. Finally, after the loop completes, the number with the highest frequency following the key is returned. To optimize our approach, several key insights come into play. First, using a dictionary for the frequency map is crucial, as it allows us to perform insertions and lookups in constant time on average. This makes it far more efficient than using a list or array, which would require linear time for updates. Additionally, we avoid unnecessary computations by focusing only on numbers that immediately follow the key, rather than comparing every possible pair of elements in the array. This targeted approach significantly reduces the computational workload. It's also important to account for edge cases, such as when the key is not present in the array or when the array is too small to have a valid number following the key. Lastly, if multiple numbers have the same maximum frequency, the algorithm ensures that the first one encountered is returned, as it naturally arises from the iteration order. To implement this algorithm, we rely on a few critical data structures and variables. The input array contains the list of integers we're analyzing. The frequency map, implemented as a dictionary, tracks how often each number follows the key. Two additional variables, max_frequency and result, are used to store the highest frequency observed and the corresponding number, respectively. When analyzing the complexity of this approach, the time complexity is O(n), where n is the length of the array. This is because we traverse the array once, and all dictionary operations like insertions and updates are O(1) on average. The space complexity is O(k), where k represents the number of distinct numbers that follow the key. This is the space required to store the dictionary, making this approach both time and space efficient. Let's walk through an example to see how the algorithm works in practice. Suppose we are given the array 1, 2, 3, 2, 4, 2, 3, 5, and the key is 2. We start by initializing an empty frequency map, a max_frequency of 0, and a result of -1. As we traverse the array, we skip indices where the current value is not the key. At index 1, we find that the value is equal to the key, so we look at the next number, 3. We update the frequency map to 3, 1, set max_frequency to 1, and update result to 3. Continuing, we find another key at index 3, with the next number being 4. The frequency map now becomes 3, 1, 4, 1. Later, at index 5, we encounter the key again, and the next number is 3. This updates the frequency map to 3, 2, 4, 1, with max_frequency updated to 2 and result remaining 3. After completing the traversal, we return 3 as the number with the highest frequency following the key. In conclusion, the number 3 is the most frequent number that follows the key 2 in the given array. It appears twice, which is more often than any other number. This example illustrates how the algorithm efficiently identifies the correct result by using a dictionary to track frequencies and by iterating through the array in a systematic way. This approach ensures that we handle all edge cases and achieve the solution with optimal time and space complexity. This Python implementation solves LeetCode problem number 2190, most frequent number following key in an array, using a simple and efficient algorithm. The goal is to find the number that most frequently follows a given key in the input array. The solution begins by importing defaultIct from the collections module. A defaultIct is used to store the frequency of numbers that appear immediately after the target key, as it simplifies handling cases where keys are not already in the dictionary. We iterate through the nums array using a for loop, stopping at the second to last element to avoid out-of-range errors. For each element, if it matches the key, the number that follows it, i.e., nums I+1, is added to the counts dictionary, and its frequency is increment. After counting all occurrences, the algorithm iterates over the dictionary to determine the number with the highest frequency. Two variables, most_frequent and max_count, are used to track the most frequent number and its count. If a number's frequency exceeds the current max_count, the most_frequent and max_count values are updated accordingly. Finally, the function returns the most_frequent number. If the key does not occur in the array or no number follows it, the most_frequent variable remains its initialized value of -1, which is returned as the result. This solution is efficient, with a time complexity of O(n), due to the single traversal of the array and dictionary, making it well suited for large inputs. This is the Java implementation of LeetCode problem number 2190, most frequent number following key in an array. The logic mirrors the provided Python implementation but uses Java-specific syntax and collections. A hash map is used to store the counts of numbers that follow the specified key. The array is traversed, and we update the map with counts. We then iterate over the map to find the number with the highest frequency. Key differences include explicit type declarations, the use of the map interface, and Java's getOrDefault method for handling default values in the map. To solve this problem, we start by initializing a defaultIct called counts to keep track of the numbers that appear immediately after the key in the array. Initially, this dictionary is empty. Then, we traverse the array while excluding the last index because there's no number after the final position. As we iterate, we check whether the current element matches the key. If it does, we look at the next element in the array and increment its count in the counts dictionary. For instance, when I is 1, the value at nums, 1, is the key, 2. The next number in the array is 3, so we increment its count, making counts equal to 3, 1. Later, when I is 3, the same process occurs, and the count of 3 increases to 2. Finally, when I is 5, the key 2 is followed by 4, so we increment the count 4, 4, resulting in counts being 3, 2, 4, 1. After completing the traversal, we identify the number with the highest frequency in counts. Comparing the counts, 3 has a count of 2, which is higher than 4's count of 1. Thus, the most frequent number following the key is 3. The result of the first example tells us that the most frequent number following the key 2 is 3. Now, in the second example, where the array contains repeated instances of the number 4 and the key is also 4, we start by initializing the counts dictionary as empty. As we iterate, we find that every instance of 4 is followed by another 4. On the first occurrence, the count 4, 4 is increment to 1. On the next iteration, it increases to 2, and finally, it reaches 3. After completing the traversal, we compare the counts in the counts dictionary. Since 4 is the only number present and its count is 3, it is the most frequent number following the key. The final output for this example is 4. In the third example, the array contains a mix of numbers, and the key is 1. We start with an empty counts dictionary. As we iterate through the array, we first find that 1 is followed by another 1, so we increment its count to 1. Then, the second one is followed by 2, so we increment the count for 2, resulting in counts being 1, 1, 2, 1. Skipping non-key elements, we find another instance of 1 later in the array, which is followed by 2 again. This increases the count of 2 to 2. After completing the traversal, we compare the counts in the counts dictionary. While 1 has a count of 1, 2 has a higher count of 2, so it becomes the most frequent number following the key. Thus, the final output for this example is 2. To analyze the time complexity of this solution, we start by examining the first step, traversing the array. The algorithm iterates through the nums array from the first element up to the second to last element, performing approximately n1 iterations where n is the length of the array. This traversal is linear, meaning it has a time complexity of O(n). During each iteration, the algorithm performs a constant time operation to check whether the current element matches the key and, if so, updates the count in the dictionary. Since dictionary operations like insertions and lookups have an average time complexity of O(1), these updates do not add significant overhead. Next, we examine the step of finding the number with the highest frequency in the dictionary. Here, the algorithm iterates over the m unique numbers in the dictionary, performing one comparison for each entry. This loop runs in O(m) time, where m is the number of unique numbers following the key. Combining these steps, the traversal takes O(n) time, and finding the maximum frequency takes O(m) time. The total time complexity is derived by summing the complexities of the two main steps, O(n), for traversing the array and O(m), for iterating through the dictionary. Since m, the number of unique numbers following the key, is usually much smaller than n in most scenarios, the time complexity is dominated by the O(n) term. Therefore, the overall time complexity of the solution is O(n). Now, looking at the space complexity, the primary contributor is the dictionary used to store the counts of numbers following the key. If there are m unique numbers that appear after the key, the dictionary will have m entries. Each entry consists of a key-value pair where the key is a number, and the value is its frequency. Thus, the memory required for this dictionary is proportional to m. Specifically, storing m keys and their corresponding values results in a space complexity of O(m). In addition to the dictionary, the algorithm uses a few scalar variables like most_frequent and max_count to keep track of the number with the highest frequency and its count. These variables require constant space, or O(1). Since the dictionary dominates the space usage, the overall space complexity of the solution is O(m), where m represents the number of unique numbers following the key. Comparing this with a naive or brute force approach, that method would involve scanning the array multiple times, once for each occurrence of the key, resulting in a time complexity of O(k*n), where k is the number of times the key appears in the array. While the space complexity for the naive approach remains O(m), the current algorithm is far more efficient in terms of time, as it processes the array in a single pass, reducing the time complexity to O(n). The current approach is optimal because it minimizes both time and space complexity. By traversing the array only once, the algorithm achieves O(n) time complexity. Using a dictionary for intermediate results allows for efficient counting operations, with each insertion and lookup taking O(1) on average. The space complexity is reduced to O(m), which is the unavoidable cost of storing counts for unique numbers following the key. Considering the best, average, and worst cases, the algorithm's performance remains consistent. In the best case, the key appears only once, and all numbers in the array are distinct. This results in O(n) time complexity, with minimal dictionary usage leading to O(1) space complexity. In the average case, the key appears multiple times, and there are m unique numbers following it. Even then, the time complexity stays O(n), and the space complexity remains O(m). In the worst case, the key appears at every position in the array except the last, and all numbers following the key are unique. Here, the dictionary will store n1 entries, where n is the length of the array, making the space complexity O(m), with m is almost equal to n1. Despite this, the time complexity remains O(n), as the algorithm still processes the array in a single pass and performs O(m) operations on the dictionary. To confirm the big O analysis, the first loop processes each element of the array exactly once, taking O(n) time. The second loop iterates over the dictionary, taking O(m) time. Thus, the total time complexity is O(n plus m). Since m is typically much smaller than n, the overall time complexity simplifies to O(n). For space complexity, the dictionary stores counts for at most m unique numbers, leading to O(m) space usage. In conclusion, this solution is both efficient and well suited to the problem, with linear time complexity and minimal additional space requirements. A common pitfall when solving this problem is neglecting edge cases. For instance, you might encounter an empty array, an array with only one element, or scenarios where the key doesn't exist in the input. Failing to handle these situations can lead to runtime errors or incorrect outputs, so it's essential to explicitly test these cases during debugging. Another issue arises when iterating through the array without properly checking index bounds. For example, accessing ARR I+1 without verifying that I+1 is valid can cause index out-of-bounds errors. To prevent this, you should always ensure that indices are within the appropriate range before accessing neighboring elements. Finally, unoptimized frequency counting is another mistake to avoid. Using a list to count frequencies, for instance, results in O(n squared) time complexity due to repeated linear searches. In contrast, dictionaries, or hash maps, allow for O(1) insertion and lookup, making them significantly more efficient for this task. Another frequent mistake is hard-coding assumptions about the input. For example, assuming the array only contains positive integers or presuming that the key is always present can lead to incorrect results if the input doesn't align with those assumptions. To avoid this, you should validate inputs and write generalized logic that can handle a broad range of scenarios. Additionally, ignoring performance trade-offs can be detrimental, especially with larger input sizes. A brute force approach may work for smaller arrays, but with inputs as large as 10 to the power of 5 elements, inefficiencies can cause timeouts in competitive programming or interviews. Recognizing when optimizations are necessary and implementing them is key to handling these situations effectively. When tackling problems like this in an interview setting, there are a few strategies to keep in mind. First, recognize common patterns, such as iterating through neighbors like ARR I+1 or ARR I1, and always be mindful of edge cases and index bounds. Hash maps are another critical tool, often used for tasks like frequency counting or mapping relationships, and their efficiency allows for O(n) solutions. It's also important to clarify input assumptions with the interviewer. For instance, ask whether the array can be empty, whether the key can appear multiple times, or even whether it might not appear at all. Discussing trade-offs between approaches can also set you apart. For example, a brute force solution might be faster to code but less efficient, while a hash map introduces extra space complexity but optimizes time. Finally, before coding, dry run your algorithm with a sample input to ensure you've accounted for all edge cases. To deepen your understanding of this problem, you can explore related problems that share similar concepts. For instance, LeetCode 697, degree of an array, involves frequency counting, while LeetCode 219, contains duplicate 2, applies a sliding window technique with a hash map. LeetCode 2025, maximum number of ways to partition an array, is an advanced problem that also uses hash map-based counting, and LeetCode 128, longest consecutive sequence, combines hash maps with array traversal for sequence analysis. Additionally, alternative approaches to solving this problem include brute force, where you iterate through the array with nested loops to count occurrences of numbers following the key. While it's simple to implement, it has a time complexity of O(n squared, and is inefficient for large inputs. On the other hand, using a hash map for frequency counting allows you to achieve O(n) time complexity by storing counts in one pass. This approach is optimized for speed but comes with the trade-off of additional space complexity. Another potential approach is the sliding window technique, which is particularly useful for problems involving fixed-size neighbor analysis. By maintaining a window that tracks the key and its neighbors, you can process the array in O(n) time. This method balances efficiency and simplicity, making it a great choice for certain variations of the problem. Similarly, the two-pointer technique can be used to track potential key matches and their neighbors. This approach is also in time complexity and is space efficient since it doesn't require extra data structures like hash maps. However, it may involve additional logic to handle edge cases, so careful implementation is necessary to avoid errors. Both of these techniques provide alternative ways to solve the problem with a focus on efficiency and adaptability to different constraints. That wraps up our discussion of this problem. We recapped the key algorithmic approach and the importance of efficient data structures like hash maps. Remember to always consider edge cases and constraints when solving problems. Thank you for watching, and we'll see you in the next walkthrough. Don't forget to like and subscribe. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!